So this is a sample problems for thermochemistry. This will get us through worksheet number 1 on energy and thermodynamics. Okay, so our first sample problem is calculate the amount of heat required to raise the temperature of 500 grams of water from 40 to 80 degrees Celsius. So you should have seen that in the notes so far we have 5 formulas altogether. We have this one and this one. This one is an easy one for figuring out kinetic energy change. You'll note that it has a delta T in it, right, which is the change in temperature. So that tells you it's kinetic energy, because remember that kinetic energy and temperature are directly related. This one is for measuring potential energy, so things like phase changes, so things from like a solid to a liquid would be an example of when we use this formula. And then there was 3 other formulas that look like this. And what you'll see is that these are a combination of these 2 formulas that we just looked at. All of these ones only happen in a calorimeter. So they're there if energy from one is lost and energy from the other is gained. So I'll show you an example of that later. But we would only use those, again, if it's happening in a calorimeter. So this one doesn't say anything about happening in a calorimeter, so that eliminates those first 3 that are equal to each other. And it does talk about having a temperature change, so that means that it's going to be this formula here. Okay, so things I look for is, first off, that you wrote out the correct formula, no matter what, right? Even if we have to change the formula around after, I'm going to look for this. This gets 1 mark. Okay, I also want to see that you actually make a list. So it says to calculate the amount of heat. That would be the H in the formula. It gives me the mass, and it's of water, so I'm just going to write H2O underneath, and 500 grams. And then it has a temperature change. And the temperature change is never going to be a negative number. It's always going to be the bigger one being subtracted from the smaller one. So, oops, sorry, other way around. So we get 40 degrees for a temperature change. Okay, so I look and see that, yes, this looks like the good formula for it. It's not changing phase. It is indeed changing temperature. So now I'm going to plug everything in. Okay, the temperature change is 40 degrees Celsius. Okay, to figure out the specific heat capacity of water, you're going to need to look on page number 3 of your data booklet, and you'll see that the specific heat capacity of water is joules per gram degree Celsius. Okay, here I'm going to be looking for everything has the units written on it, everything is written in the right place. Okay, then you go ahead and you do this. So when I do this, I get this number from my calculator. Grams cancels off grams, degrees Celsius cancels off degrees Celsius, and I would get joules. Okay, when I look at this number, this one has 4 sig figs, this one has 3 sig figs, and this one has 4 sig figs. So my answer should only have, this one I think is supposed to be a 0 actually, so it should have 4 sig figs. So 4 should be my answer. So I can write it a couple ways. I can write it in scientific notation. So that would be 8.38 times 10 to the 4th joules. I could write it in kilojoules by moving the decimal place over 3. Okay, make sure that you circle your answers. I'm going to be looking to see whether or not you have your answer in the least number of sig figs. I'm going to be looking to see whether or not you have the units. Okay, again, if you have your formula to begin with, and if you've plugged your numbers in. Great. Next question. Calculate the amount of heat required to raise the temperature of 10 grams of gold from 20 degrees Celsius to 200 degrees. I think this is actually supposed to be a degree symbol is what that is. Okay, so calculate the amount of heat, and it has a mass of gold and a temperature change of 180, right, by doing 200 minus 20. Okay, again, it can only be H equals NH or H equals MC delta T, so because it has a temperature change, it's going to have to be this one. So we have 10 grams Okay, now they didn't give me the specific heat capacity of gold, so I'm going to have to use my data booklet, and we're looking for, it's usually the second last page in the data booklet. It has thermodynamic properties of selected elements on it, and it's in alphabetical order, and you'll see that the specific heat capacity of gold is this. You'll notice that all metals have their own specific heat capacity. You notice the difference between just any metal and water's heat capacity. Water has a huge heat capacity. Okay, so when we do this on our calculator, we get 232.2, right? And that would be joules. Okay, looking at sig figs, this has 3, this one has 4, this one has 3, so my answer should have 3. So I'm just going to write this as my answer. Great, next question. Okay, this one says calculate the amount of heat required to raise the temperature of 200 milliliters. So important fact here is that 1 milliliter of water equals 1 gram of water. It's just assume that you know that. Okay, and we're going to calculate the heat again. We have a mass of water then that is 200 milliliters, which actually equals 200 grams, and we have a temperature change of 30 degrees Celsius. Okay, so now we have 200 times 4.19 times 30. So we get this number. Okay, this is in joules. This number has 4 sig figs, this one has 4, this one has 2, so my answer should only have 2. So I'm going to change it to kilojoules by moving it 1, 2, 3 spaces. So that means 25 kilojoules is my answer. Next one, calculate the amount of heat lost when 5 grams of copper cools from 75 to 25. So again, heat, we have a mass of 5 grams, temperature change of 50 degrees Celsius, and we need a specific heat capacity of copper. So looking on that data booklet page, I see that copper is 0.385. Okay, so you might want to pause the video here and see if you can come up with the formula, see if you can come up with the right answer before I do. So the formula would be MC delta T because we have a temperature change. We have 5 grams times 0.385 and the temperature change of 50 degrees Celsius. Okay, so this is what my calculator reads, but again, we only want to have 3 sig figs, so we're going to write 96.3 joules. Okay, next question. This one you can see is a scary looking question, right? Because it has so much stuff to it. So first off, let's make sure that we write out everything that we need. So it says calculate the specific heat capacity. So remember from our notes that's C, right? So we need to do that of nickel. We're going to pretend like we don't have the data booklet that we could look it up in. Okay, the next one is that we have a mass of nickel that is 146.8. And we have a temperature change of nickel. So the nickel started at 83.7, and once you go down, you'll actually see that the temperature of the system is 22. What that means is that the nickel started off at 83.7, right? I dropped it into some water. The water was at 17.2. So the water was at 17.2. And what you expect, right, is if I drop hot piece of metal into water, that the water will increase in temperature, and that's exactly what happens, right? So not only does the water end up at 22 after, but the copper also ends up at 22. Okay, so again, notice that the 22 is in different places when we're figuring out the temperature change, right? Because here, this was at a greater temperature to start with. So the temperature change is 61.7. Here, the temperature change was increased, right? So that would be 4.8. Okay, and then we have a mass of water that is 200 grams. And we know the specific heat capacity of water is 4.19 joules per gram degree Celsius. Okay, so now we have three choices. What we'll see is that the water was changing temperature, right? So that's kind of this formula. So this one is for the water. But we also have the nickel changing temperature, so that's like this. So what happens is essentially that the energy lost by the nickel actually goes to the water because it's in a closed system. So the way we show that is by doing this. And we let this side be the water side and this side be the nickel side. Okay, we're trying to figure this out. So that means that we manipulate the formula so that we have the MC delta T of the water divided by the M and delta T of the nickel. Okay, I want to see this one. I want to see this one. I want to see this. So I want to see the actual manipulated formula, and then you can stick the stuff in. So make sure that you put the right mass in the right place. So we have 200 grams of water, the specific heat capacity of water, and the temperature change of water, all divided by the mass of nickel times the temperature change of nickel. So it's going to look like this. So my calculator reads 0.444093112, right? So we only want to have 3 sig figs by looking at this, right? The least number of sig figs, so it would be 0.44. Okay, notice that grams cancels off grams, degrees Celsius cancels off degrees Celsius, so I get joules per gram degree Celsius. Okay, in this question what we're doing is it's called a heating or cooling curve. So in this question, when I give it to you on a test or a quiz, it's actually going to look like this one that is down here. So it's actually going to look like this. Just for this case, I've actually written it out in the 5 steps that it actually takes. But again, it will look like this. And it's just assumed that you know that it actually takes the 5 steps. And again, this is either called a heating curve or a cooling curve. Okay, because this one is actually 5 steps, again, and this one is actually going from, you'll see it goes from ice to steam. This one is actually called the heating curve, so that's actually what's happening. Okay, so I'm going to do this on another page just so that we have lots of room for it. So if you need to copy down this question, you can copy that down. I'll write it again at the bottom of the next one. Okay, so again, this is more like what the question's going to look like. And again, I can see that it has to go from being a piece of ice to a piece of steam. So that gives me a hint that it's actually a heating curve. Okay, in step number 1, what we have is H equals MC delta T. Because I'm going to draw kind of a graph as we go along with this. But this is often part of the question too. This would be my heating curve. And what I have over here is I'm going to have temperature and it's measured in degrees Celsius, and over here I'm going to have energy. Okay, so what we started off is at minus 40 degrees Celsius. Okay, and it's going to raise up to 0 degrees Celsius. So what we're doing is we're figuring out this right here. This is step number 1. When I'm talking about the phase of it right now, it's a solid. And because it's changing temperature, and I can see that it's going from minus 40 to 0, that is a kinetic energy change. Okay, anytime we do kinetic energy change, remember that we use this formula, this H equals mc delta T, because remember that kinetic energy and temperature are directly related, right? If one goes up, the other one goes up. If one goes down, the other one goes down. Okay, so the mass is 100 grams. The specific heat capacity, now we've been using 4.19 for many things, but we need to have the specific heat capacity of ice. So if you look in your data booklet on the very last page, what you'll see is that the very first thing actually listed is H2O solid, and what we're looking for is the specific heat capacity, which is in the very end column, and it says 2.00 grams per degree Celsius. Okay, and next we need the temperature change. So if it went from minus 40 to 40, that is a 40-degree temperature change. Again, no negative temperatures, right? It's always going to be a positive number. Okay? Okay, so here we're going to have that it's 8,000 joules, right? I'm going to change it to kilojoules also, which would be 8.00 kilojoules, and I'll show you why afterwards, but we're going to change it to 8.00 kilojoules. Okay, so now we got just this first step figured out. Now we're on step number 2. What happens at step number 2 is remember that it undergoes a phase change. So it goes from being a solid to a liquid now. And this is a potential energy change. Anytime we're trying to measure potential energy in thermodynamics, we're going to use this formula. So H equals NH. Okay, so this one is always for potential energy and for phase changes. So we don't actually have the number of moles in the question, right? So first off, we're going to have to replace the N with mass divided by molar mass, because that's how we find the number of moles. Okay, and then we're going to have the mass of it is 100 grams. On the side, we might need to figure out the molar mass one time. It is expected that you guys know how to figure out molar mass because this is a higher level of chemistry, right? And this is like grade 10 stuff to figure out molar mass, but make sure that you can do it. So molar mass is there's 2 hydrogens. Okay, I look up what 1 hydrogen weighs, and this is on the data table, so very out in the first periodic table it's actually there. So you'll see that 1 hydrogen is 1.01, and we have 2 of them, so that means it's 2.02. We have 1 oxygen. 1 oxygen weighs 16 grams per mole. So that would be 16, okay? And then I add them together to get 18.02. So the molar mass is 18.02 grams per mole. Okay, so by doing this, you notice that grams cancel off grams, and I'm just left with moles, so I can actually see that, right? Next, I need this, which is called the molar heat. So sometimes it's called the molar heat of vaporization. Sometimes it's called the molar heat of fusion. Sometimes it's called the molar heat of evaporation. Sometimes it's called just molar heat. But you need to know that capital H is molar heat. Sometimes it's called the molar heat of reaction. Okay, we need the molar heat for when a solid turns to a liquid. So again, on the very last page of your data booklet, you'll see that we're looking for the molar heat of fusion. And so you'll see that the number is 6.01 kilojoules per mole. Okay, moles cancels off moles. Okay, so now we're going to do that on our calculator. So make sure that you do 100 divided by 18.02 first. And then you're going to times it by 6.01. And we're going to write down the whole number that we have. Notice that this one is actually going to be measured in kilojoules this time already, so that's good. Okay, now we're going to go on to step number 3. Step number 3, you'll see from up here, is now when we have water that's a liquid at 0, now it can actually go to being at 100 degrees Celsius. We're only ever going to do this with water. We're not going to do it with anything else because I only expect that you know where water boils and where water freezes. Okay, this is a kinetic energy change again because it is changing temperature. So we'll go back. Okay, because it is a kinetic energy change, we're going to go mc delta T. And the mass is still 100 grams. The specific heat capacity now is going to be of water, so it'll be joules per gram degrees Celsius. The temperature change is going to be 100 degrees, right, because it went from being at 0 to 100. Okay, and so what we have is 100 times 4.19 times another 100, right? Remember that this is going to be in joules, because grams cancels off grams, degrees Celsius cancels off degrees Celsius. I'm going to change it to kilojoules. So there's my number 3. Okay, now we're going to go on to number 4. So just so you can see, now number 4 is going to be right here. So what happens here is now it changes from being a liquid to a gas. Okay, and this is a potential energy change because it is a phase change. So we're going to figure out how much energy that takes. So number 4 would be this formula because again this is for potential energy. So we're going to go with 100 grams divided by 18.02 again so that we can figure out the number of moles. And this time we're going to take the molar heat of vaporization, which we'll find in the data booklet again on that last page, and it looks like this. Okay, notice that grams cancels off grams, moles cancels off moles. So we're going to do this now. So 100 divided by 18.02 and then times it by 40.65. So we should get 225.582689 kilojoules. Okay, now we'll go back, look at it one more time. Okay, so now we are on to step number 5. So step number 5 is right here. What happens is that it's actually raising to 120 degrees. So when it does that, it's still a gas. This would be a kinetic energy change. Okay, so this is step number 5 now. This one was 4, this was 3, this was 2. Okay, so now we're going to figure out how much energy it takes to do that last little one. So we'll do it over here. Step number 5, because it's changing temperature, that means that it's a kinetic energy change. It's still 100 grams. This time we need, now it's steam, right? So we need the specific heat capacity of steam. So if we look on our last page again, you'll see that the specific heat capacity of steam is 2.02. Okay, and now the temperature change is only 20 degrees, right? Because it went from being at 100 to now being at 20. So now we'll do this one on our calculator. And we get this, which is in joules, and we want to change it to kilojoules. Okay, notice that I am not rounding any numbers right now. I don't actually round until the very end because we want to take the total of the numbers and add them together, so we don't want to lose any significance. Okay, so now what I'm going to do is I'm going to go back and I'm going to add all my numbers together. So here, so it's really kind of like a step number 6. I'm going to add all together. So I'm going to do the ones I can see right now. So there's this one, There's 225.582685.9. There's the 41.900. There's 33.351813. Oops. And 8. Okay, we're going to add all of those together. So it says 312.8745.172. Okay, when I look at the number of decimal places here, the least number of decimal places is actually 2 decimal places. And so that means that I should have 2 decimal places on my answer. Doesn't have 2. Two decimal places. So I should have 2 decimal places in my answer. So that would mean that it's 87 kilojoules is the total amount. Okay, now not only will the question be like this one at the beginning, so it'll just say calculate the amount of energy to take it to rise, and you are expected to know that that takes 5 steps and know the 5 steps. The other thing is that I will often ask for you to draw me a heating or cooling curve that fits with this. I want to make note that when I ask you to draw them, I'll ask you to draw it very similar to what's here. So I'm going to ask for the phases of everything, so whether it's a solid, whether it's changing from solid to liquid. I'm going to ask for whether it's a kinetic energy change or a potential energy change. I'm going to ask for all the axes to be labeled. I'm going to ask for a title. So it should look just like the one that we've just drawn. Okay, the opposite of a heating curve is a cooling curve. So that would be the same kind of question, just drawn backwards. So make sure that you have a look at the worksheets and try some of them. 4H is an example of one that's on the worksheet. When you do a test, you'll get a data booklet, right? So I won't expect you to memorize like all these numbers that came from the data booklet, but you do know how to have to be able to find them all. Okay, next slide. Okay, I just wanted to do one more question. So this one actually comes right directly from your worksheet. It's 4A. This one says calculate the amount of heat needed to vaporize 2 grams of sodium metal. So first off, I have to calculate the amount of heat. I have a mass of sodium, which is 2 grams, and the molar heat of vaporization, that means the capital H. Anytime it says molar heat, that's talking about the molar enthalpy, or the capital H, is 101 kilojoules per mole. Okay, there's nothing about temperature change, so that means that this is not even a possibility, right? Nor is any of the ones that we looked at for calorimeter, because they would all be in a calorimeter and something has to be losing and something has to be gaining, and this one doesn't say anything about that. So that leaves only this formula left. So we take the mass of sodium, which is 2 grams. Then I'm going to have to figure out what the molar mass of sodium is by looking at my data booklet, and I'm going to see that 1 sodium weighs 22.99 grams per mole, and they actually gave me the molar heat of sodium here, so we do this. So grams cancels off grams, moles cancels off moles, and I'm going to end up with kilojoules. So make sure that you do the 2 divided by 22.99 first, and then times it by 101. Okay, as far as sig figs go, there should be 3, so it should be 8.7, and this is actually what's on my calculator. Missing 1/8 there. Okay, but I only want 3, right? So that's here, so the number next to it actually makes it round up, so it's 2.79 kilojoules. Great. Okay, next we're going to do potential energy diagrams in another video. So again, you should be able to do the whole first worksheet.